everyone, welcome to ExamRat. My name is Shatabdi, I'm a medical student. Today we're going to be talking about sound, and we've already done our class on it. If you haven't watched it yet, you can easily go to our YouTube channel and watch it. Let's have a quick recap about what we had studied the last day. We had studied about the definition of sound, how it is an energy which produces the sensation of hearing in our ears. We had talked about that sound always travels through a medium and that it cannot transmit in a place where there is no medium, that is when there is no air molecules or water molecules or solid molecules, that is sound cannot travel in vacuum. Okay. We had talked about how sound is a longitudinal wave. It travels via compressions and rarefactions. We talked about that sound also travels in the form of transverse waves in solids sometimes. And we had also talked about how when we plot down the compressions and rarefactions in the form of a graph, it comes something like this. We had talked about its characteristic features, the characteristic features of a sound wave. We've talked about amplitude. We talked about wavelength. It is how the length, the distance traveled by sound to complete one oscillation. We talked about amplitude, how it was the maximum peaks of the most dense portion of the sound or the most sparsely dense portion of the sound, and when plotted in a map it will be something of this sort, like the compressions plotted together will form the crests and the rarefactions plotted together will form the trough of the sound wave. We talked about frequency. What I didn't tell you is that the unit of frequency was 1 by time period, right? So it is seconds to the power minus 1, which we write it as hertz. So hertz is the SI unit of frequency. Okay. We also talked about the different characteristics of sound, like the characteristic properties, which were loudness, pitch, and quality. So now loudness, we had talked about how it depended on amplitude. More the amplitude, more will be the loudness. We talked about pitch and how it is related to frequency. So the sounds which are more frequency, they will be shrilled. And quality was something that did not depend upon any of the physical characteristics of the sound wave. It did not depend on amplitude or frequency. It was something that was very qualitative, subjective, and we had used the example of how two sounds coming from a guitar and a flute, even if they somehow have been made of the same amplitude and frequency, they will still never sound the same. The same case can also be that when you use two guitars, even if they are identical, the sounds coming through them will always be different. So that was how we defined quality. Okay. So today we are going to talk about the speed of sound through different media. Now what does it say? These are some important points. If you want, you can pause the video and you can take it down. So it says that the speed of sound depends on the properties of the medium through which it travels. Obviously, like in gases, the molecules are very sparsely packed, right? But in solids, they are very closely packed. So obviously, there will be a difference. The speed of sound in a medium depends on the temperature of the medium. Okay, we'll come to this later. And the speed of sound decreases when we go from solid to gaseous state. Okay. So, by this example that I gave you of gases and solid, I hope it's clear like why this third point is being made, that the speed of sound decreases when we go from solid to gaseous state. So obviously the amount of time that this gas molecule is taking to vibrate and transmit the energy to the next gas molecule, at the same time, since in solid the molecules are so densely packed that the transmission takes place very fast, right? So as a result of which, the sound will always travel faster in solid than in gaseous state. Simple. Okay. Temperature is also kind of the same logic. It is that when you are increasing the temperature of something, what is exactly happening? It means that the molecules present inside the object, they start vibrating at a very high speed, right? A very high speed as opposed to the one it was vibrating before. So due to this increased vibration, increased magnitude of vibration rather, they will oscillate at a much higher speed, right? And they will oscillate, and as a result of which they will also transmit the energy much faster. So increase in the amount of vibration will lead to increase in the transmission of sound, right? So that is why it is said that that more you increase the temperature, the faster the sound will travel through that medium. So these are the 2 points that you have to memorize. Okay. Now we talk about a very interesting topic, that is reflection of sound. So it says that like light, sound gets reflected at the surface of a solid or a liquid and follows the same laws of reflection. Okay. So in case you don't have the idea about the reflection of light, I'll just draw it for you. So here, let this be a polished surface. So right now, remember that we are talking about light. So when we talk about light, we obviously need a polished surface for reflection. For sound, it does not matter if the reflector is rough or polished, but for light, it is a prerequisite. Okay. So let's draw a normal. It's not exactly a normal. Okay. So just pretend that it is straight. So now what's happening is that an incident light is coming. Just pretend that it is straight. Okay. So yeah. An incident light falls on it, falls on the mirror, and it gets reflected. Okay. So basically, the angle of incidence will always be equal to the angle of emergence, or the angle of reflection rather. Just call it R. So the law of reflection says that angle I is always equals to angle R, provided that the point of incidence, the point of reflection, the point at which the normal is produced are all in the same plane. Okay. So the sound is incident. So here, when we talk about sound, what they are writing is that the directions in which the sound is incident and is reflected make equal angles with the normal to the reflecting surface at the point of incidence, and the three are in the same plane. So it means that it is the same as the law of reflection of light, that angle I equals to angle R, and all the three are in the same plane. Okay. So now, why is this important? Like, why are we talking about the reflection of the sound? Because this gives the basis of echo. So now, what is an echo? Echo is a sound or sounds caused by the reflection of sound waves from a surface back to the listener. Okay. So suppose you are standing in front of a huge wall and you are clapping. So when that happens, as you can see that the sound is traveling to the wall, it is getting reflected by an equal angle. If you draw an imaginary normal here, you will see that angle I equals to angle R, and the sound is getting reflected at the same angle and coming back to the listener. So how many sound is the listener listening? It is basically two sounds, right? Like one when it's hitting the wall, like immediately after the sound is produced, one you hear sound number one, and the second one you hear after it is reflected back. Okay. So what is the condition of an echo? Like if the wall was here, for example, if the wall was here, then would the echo have been possible? So what does the echo depend on? So basically it says here that to hear a distinct echo, the time interval between the original sound and the reflected sound must be at least 0.1 seconds. So if this time of going and coming back, if this whole time taken is less than, if the total time taken is less than 0.1 second, then what does it mean? It means that the echo will not take place, because you minimum have to listen the sound after 1.1 second. That means that the time taken has to be greater than 0.1 second for it to be called an echo. So that is why it always has to be at a particular distance. So now what is the distance? It is basically said that, suppose you know that the sound through air, the speed of sound through air is 330 meter per second. Okay, 330 meter per second is the speed of sound. So now what's happening is that if you calculate, so what is coming? It is basically, another thing that you have to remember is that if the sound is going and then coming back, then what is the distance that it is covering? Not displacement, because displacement is 0, but what is the distance? It is twice the distance between you and the wall, right? So whenever you're calculating the speed, it will basically be 2d by t, right? Because you are covering twice the distance for the echo to be heard. Okay. So now this will come as d equals to s into t by 2. And you know s here is the speed of the sound, which is 330, into time is 0.1 second. We are taking like the minimum for which the echo can be heard, divided by 2, right? So basically this will come at 17.5 meter or 16.5 meter roughly. 16.5 meter. So basically for an echo to be heard, so basically for an echo to be heard, the minimum distance that the sound has to travel is 16.5 meter. Okay. Or you can say that for an echo to be heard, it should be heard after a minimum time interval of 0.1 seconds. Okay. So now that we have understood the concept of echo, let's go over reverberation. So echo was basically reflection once, right? Like you're clapping, like you are standing on a mountain cliff, for example. Like here you're clapping, then it gets reflected and it comes back to you. Okay, so this was the concept of echo, where it was just the reflection was just happening once. Reverberation is one step ahead. It is the repeated reflection that results in the persistence of sound. So, repeated reflection. So, what does it say? It means that when you are present in a huge hall, okay, like a huge ceremonial hall or a huge conference hall, and you are here. So, whenever you're producing a sound, what is happening is it is not just undergoing one reflection, it is going multiple reflections. So it gets reflected here, then here, then here, then again coming back. So there's a repeated reflection. So now what is happening is that each time the reflection is happening, you are able to hear the sound, right? So, and since the distance, like since the point of the reflection is every time different, so when you accumulate all the reflections, you hear a standing sound for a longer period of time, right? So this means that all these reflections take a lot of time. Like as opposed to echo, when it was just you were clapping and then you were hearing the sound and that was it. But here it goes on for quite a while. So in echoes, the only difference between a reverberation and an echo is that an echo, the reflection happens once, and here in reverberation, the reflection of sound happens multiple times before ultimately the density of the sound or the intensity of the sound decreases and it comes to a stop. Okay. So we studied about the reflection of the sound. We've studied about some interesting concepts like echo or reverberation. So what are the applications? So the applications are basically that megaphones or loud hailers, horns, musical instruments such as trumpets, they are all designed to send sound in a particular direction without spreading it in all directions. So what does this mean? So this is, for example, a megaphone or a horn. So this diagram here is basically the mechanism behind it. So as you can see here, that once the sound is produced here, the number of reflections that are taking place, right? At least 10. Okay. So as a result of this, the sound that you are hearing is much louder, because since it is a confined space, the intensity of the sound is not decreasing, as opposed to when we were just speaking in a hall, like you're one person present, you're speaking in a hall, the reverberations, like the reflections for the reverberations are taking a longer period of time, right? So when it is traveling from one point to another, its intensity is automatically decreasing because there's air friction, there's a lot of other factors. But when it is a confined space like that of a trumpet, as you can see that there are not, like it does not take that much time to be reflected, right? Like it's happening immediately within milliseconds. So that is why the intensity is remaining intact. So when you are hearing it, not only is it loud, it is also in that particular space that you're hearing. So this will not go like this. Like this will not be heard throughout the entire region, but it will just be enough to produce an optimal sound, with as opposed to the amount of sound that you are producing here. Now if you speak very loudly here, so obviously you'll get a much louder sound which will be spread to a much larger area. But if you make a normal optimal sound, then it will be intensified, but only it will confined in a particular region. Okay. So this is one of the examples that I took. Another example, like surely if you're following the NCERT books or the other books, you'll find a lot of examples there. Another small example is that, like, the stethoscope. Okay, the stethoscope that doctors use, that is also based on a similar concept. So it looks something like this. Here is the bell and this is the diaphragm. Okay. So again, what is happening is that if you place it here on top of your heart, then obviously the heart is beating every second, right? So the vibrations are being produced, and from the diaphragm is picking up on that vibration. The diaphragm present here, it's picking up on that vibration, as a result of which it is transmitting the sound in a very confined space. Now, as it was happening here also, here the same thing will happen, that is, the sound is being reflected very fast, so the intensity is remaining the same, so that when it reaches the doctor's ears, the intensity is exactly the same, if not more, and it is confined only to the ear, right? Like if you stand here, you won't be able to hear it, only the doctor is being able to hear it inside his ear. So it is the similar concept as that of a megaphone. Okay, now ultrasound. Before ultrasound, one thing that I want to discuss is that human ears have a range of frequency in between which they can hear the sound. So the range of human ear is basically 20 hertz to 20,000 hertz. So in between this, if in between this frequency, if a sound is produced and the human ear is able to hear it, if it is less than 20 hertz, it's inaudible to our ears, and if it is more than 20 hertz, then also it is not possible for us to hear. So ultrasound they are basically high frequency waves. Ultra, when we are talking about ultra, it means more than 20,000. Okay, so yeah, so more than 20,000, it means that we cannot hear it. So ultrasound or the ultrasonic waves, we cannot hear it. And if it was less than, sorry, yeah, and if it was less than 20,000, then also we wouldn't be able to hear it. And less than 20,000 is basically, sorry, less than 20 hertz, sorry, my mistake. So less than 20 hertz is basically called infrasonic. And this is ultrasonic. So a question might arise in your minds that if we cannot hear the ultrasonic waves, then what is the use of it, right? So the use of it is basically not for us being able to hear it, but the fact that they are very high frequency waves, it means that they cause a immense amount of vibrations. So ultrasounds are able to travel along well-defined paths even in the presence of obstacles. They are used extensively in industries and for medical purposes. So not only do they produce a vibration of a huge magnitude, they are also able to travel along well-defined paths. So it does not matter if there are obstacles like walls and stuff present, it can penetrate through them. Why? Because it has a huge frequency. like more than 20,000 hertz, like 40, 50, 60 even. So that is a huge number. So it can penetrate through any obstacle. So they are usually used to clean parts located in hard to reach places, such as spiral tube, odd shaped parts, electrical components. So what exactly happens here is that you take a container, you place that object, okay, and mind you, you have to place it in a solution, okay. So why in a solution or why in a liquid part? Because I told you that sound waves travel very, very fast as compared to in gases, right? Like the molecules are sparsely placed, but in fluids they are comparatively closer to each other. So we place the cleaning object in a solution, and then what we do is we produce ultrasonic waves here. So it vibrates with a huge frequency, this whole solution, which is obviously transferred to the cleaning object as well. So the fact that the cleaning object is vibrating in at a huge space. So when we discussed about inertia, I had told you that sometimes, like the dust particles or anything that is present inside a carpet or inside an object, their the uh, their sense of change of inertia, that the fact that they have to change their state of rest to motion, takes longer time by within which the object has already moved. So since this object is moving at such a high frequency, because ultrasonic waves are produced in it, so you can imagine that it takes, like within seconds, the object is moving like at a speed of 40 or 50 meter per second, right? So it is not possible for the dust particles to move alongside the particles, so they just stay static when the object has moved, as a result of which they fall down and they are contained in the solution. So due to their high frequency, the particles of dust, grease and dirt get detached and drop out. The objects get thoroughly cleaned. Very simple. Okay. Another example of ultrasound is that you have heard it like USG, when a fetus is being grown inside the uterus. So this is the uterus. Fetus is being grown here. So what is happening is that when you are doing the ultrasound here, you are again producing high frequency waves, right? Waves that are not audible to us for obvious reasons, but what is happening is that the waves are penetrating through your skin. Why? Because we said that since they are high frequency waves and they also are able to travel along well-defined paths even in the presence of obstacles. Here the obstacle being the skin. So what happens is that they penetrate through the skin, through the tissue, the fascia, and they reach the amniotic fluid present here. Just use a different color. So if this is the amniotic fluid and this is the fetus, so the concept is same, that we are being able to locate the position of the waves when they are getting reflected and how they are coming back. So what is happening is that a screen which is attached to the USG cable, we can sort of see the whole thing happening inside, because the ultrasonic waves have been transmitted and been reflected back and they are giving us a report on it. So that is again another use of ultrasonic waves, in which we can locate the position of the fetus, and if by chance there is a problem that is detected, then it can be fixed as well. So this is that will be all for today. We have talked about ultrasound here, which is a very interesting concept, but also you have to study a bit because questions come like the applications of ultrasound mostly. We've talked about how it's used in megaphones, loud hailers, horns, musical instruments, also stethoscope. Stethoscope. Yeah. We've talked about reverberation. You can actually do a small experiment, like whenever you go to like a huge hall for like a marriage ceremony or anything, you can just go to a quiet. It will actually also work in a large washroom also, so you can just experience it. And echoes also. Oh, we've done like forever since we've gone to mountains, and we've always tried this. Like we've shouted our name and just come back to us. Talked about the basis of this whole echo and reverberation that comes from the reflection of sound. The law of reflection, which is very important, it is asked a lot. And last but not the least, we talked about the speed of sound through different media, how it differs from medium to medium, how it depends upon the temperature as well as the state of the medium. Okay. So the next day we will discuss a little about sonar. We will discuss about the human ear and how exactly the sound is traveled, like you produce the sound and how exactly it is traveled inside the ear, and not only that, how it is then transmitted through the brain. We will talk about this, and then we will just go over through some questions and we'll be done with this chapter. So thank you for your patience, and keep watching.